Good afternoon. We are filming a video lesson for our unit on plate tectonics. There's already one video lesson available to you guys, which is all about the plate boundaries. That is something we will do in class together, but that video lesson was created 2 or 3 years ago. It's already ready. Okay, so new video lessons for this unit for our COVID year, doing hybrid classes. So plate tectonics is very important. That's why we will spend, well, we're going to spend basically 2.5 weeks on plate tectonics, 1.5 weeks on volcanoes, and then have our exam after 4 weeks of class. So that'll be sometime in, I guess, October. All right, so we'll begin with the important ages I'm going to want you guys to know for your third exam. Third exam is pretty hefty, by the way. All right, the age of the universe, about 13.8 billion years. Don't forget the capital G, little a, just refers to billions of years. Age of the Earth, 4.57 billion years. And how do we know the age of the Earth? Well, we're going to get to that. Age of the oldest continental crust is only 3.96 billion. Okay, so notice there's a discrepancy there. So there's something that we find that gives us an age date of 4.57 billion, even if it's not the oldest rock ever found on this planet that originated on this planet. Can you imagine what that might be? If you said meteorites, you would be correct. Meteorites give us an age of 4.57 billion years. So that age is good not only for planet Earth, but for the whole solar system. Okay, age of the oldest oceanic crust, actually still in an ocean basin, is very young. It's only 180 million years. Remember that capital M, lowercase a, refers to millions of years. So there's a big discrepancy there. We could say that oceanic crust does not make it into old age. Why is that? Well, we're going to learn that in our lesson on plate boundaries. Something's going to happen to the oceanic crust to make it not make it into old age. All right, a couple other things here. Oceanic crust is more dense than continental crust, and continental crust is thicker than oceanic crust. I'm putting the camera down for a second and walking over here because I just realized that I forgot to give us a rock type for each of these crusts. Oops. Okay, back to where we left off. All right, oceanic crust, which is made of basalt, dark mafic igneous rock, is more dense than continental crust, which is primarily made of granite. Granite is a felsic, intrusive igneous rock. So, another important point here is that continental crust, while it is less dense than oceanic crust, it's actually thicker than oceanic crust. And when you watch the narrated PowerPoints, you will see what I mean there. I'm going to want you to know the average thicknesses of the two different types of crust and the two different types of lithospheric plates. All right, so moving over here, let's adjust the iris a little bit. Nope, that's zooming. Okay, let's adjust the iris a little bit. It's awful bright here. All right, and maybe we could zoom out just a tiny bit. Okay, so what we're looking at here is a giant slice of the planet Earth. Basically, we're trying to describe the interior of planet Earth. We will do this in class together. Pretty sure we'll have time for that. So this video is going to be useful for anybody in quarantine, and even those of you that come to class and get to see this in person, it's still useful to review this before taking the exam. So notice it's kind of like a slice of pie or pizza. Okay, so we're going to start at the bottom where it's kind of pointy. Okay, so at the bottom, or at the center of the Earth, we find the inner core. So you probably learned core, mantle, crust when you were in your K through 12 experience. It's actually a little more interesting than that. There's an inner core and an outer core, and it's not just about the crust when we get to the top. So the inner core is solid. It's made of iron and nickel. So it's basically a solid ball of metal. Now, surrounding the inner core, we have the outer core, and it, believe it or not, is liquid metal. We don't expect things to be liquid at such deep depths within planet Earth because of pressures, but indeed the outer core is liquid. We know for a fact. That's why we have an electromagnetic field protecting the life here on this planet. I will expect you guys to watch the narrated PowerPoint for this lesson, which I hope to create this weekend, and we'll discuss how we know the outer core is liquid. Okay, then we have the thickest layer, which is known as the mantle. So it's indeed the thickest layer. It's primarily made of olivine, which is a greenish mineral. And as far as its composition goes, or its behavior, we're going to say that it is solid. We refer to it as the rocky mantle, but it does very slowly have convective heat flow with time. Okay, now notice that as you move up in the mantle, you have a dashed line, your first of two dashed lines. Dashed lines mean something. It means it's not necessarily going completely from one layer to another, but just some kind of boundary. So above that first dash line, the lowest dash line, we have something referred to as the asthenosphere. So the asthenosphere is part of the mantle, but it behaves differently. Therefore, we give it its own separate name, the asthenosphere. We could think of it as the upper mantle, and it behaves as a plastic. So it's not molten. It is not magma, but it is actually going to flow and move and yeah, it's going to flow with time, very slowly with time, deform with time, we might say. Okay, so now we're going to move towards the top of our slice of pizza here. So now you have another thick line there. So what I want to call your attention to here is, and I'm really glad that I bought some different colored markers over the holiday weekend because it helps with this drawing, I think. So in the brown brackets on either side there, notice the brown brackets are encompassing two layers there on top. So within the brown brackets, we refer to that as the lithospheric plates. I'm going to move the camera just a little bit so you can see what's written here in the top right of the board. We refer to these things on top as the lithospheric plates. Sometimes we just refer to it as the lithosphere. Sometimes we just refer to them as the plates. Now the plates are going to behave in a rigid or rocky manner, meaning they are solid and they will very slowly move across the plastically behaving asthenosphere. All right, so back to our plates. You're going to notice that towards the top there we have another dashed line. So that dashed line in purple, or pointing to it, we call that the MOHO, M-O-H-O. The MOHO, you're going to need to know what that means. It is the crust/lithospheric mantle boundary. I forgot an arrow. We're going to put the camera down for another second, and I have to add in one more arrow before we finish our discussion here. Okay, back to where we were. So above the asthenosphere, we find the plates, lithospheric plates. Now the plates consist of two different parts. Okay, on the top we have the crust, and on the bottom of the plate, the thicker portion of the plate, we're going to refer to that as the lithospheric mantle. So that purple dashed line in there is called the MOHO, and again that is the crust/lithospheric mantle boundary. Okay, so back to the crustal portion. So the very top of our plate, what we are walking around on, is referred to as the crust. There's two different types of crust. There's continental crust and there's oceanic crust. So you see there's a vertical purple line there kind of breaking that crust into two parts. What else do we see in this drawing? Well, notice there's an elevation change where basically, let's say that this is North Carolina mountains to the sea. mountains over there on the far left, and then coming down to the coastal plain, and then there where you see the ocean water, we'll say that that is Wrightsville Beach. So offshore, say maybe towards closer to the edge of the chute. We're gonna have to walk over here and make the stupid light come back on. All right. I really need an assistant. Okay, back to where we were. All right, so let's say offshore a little bit, like maybe getting closer towards the edge of the continental shelf, moving on down the continental slope. There we will transition from continental crust into oceanic crust. Okay, so every plate on the planet is going to consist of crust and lithospheric mantle. There are several plates on this planet, by the way. And the plates are either going to have continental crust, oceanic crust, or some of both. In this drawing, we don't have a plate boundary here. Okay, so again, this is western portion of North Carolina in the mountains, going down to the coastline, and then offshore, kind of heading out there towards the middle of the Atlantic Ocean. So just to remind us, something that we filmed earlier in this lesson on the other board, continental crust, what's the primary rock type there? Granite. Oceanic crust, what is the primary rock type there? Basalt. Now, we always do plate tectonics after we get finished with all the minerals and rock types. So yes, we spent some time talking about sedimentary rocks and weathering. So in our continental portions of the crust, yes, we do find some sedimentary rocks, but they tend to be towards the top, and they're not making up the majority of the continental crust. The majority of the continental crust by far is granite. All right, so let's just back up a little bit. Hopefully it'll stay in focus. Okay, so this drawing, trying to show the whole thing here, are you going to need to know this drawing for your exam, your third exam? Yes, you're going to have this drawing, and I'm going to have the different layers listed, and you're going to have to match them up for me. I'm going to have to answer some questions, such as inner core, solid or liquid, outer core, solid or liquid. What's the dominant mineral in the mantle? How does the asthenosphere behave? How do the plates behave? All right, you're going to need to know all of this. So that'll do it for this short lesson on interior of the Earth.